Space, the final frontier. These are the voyages. Hang on, that's not why we're here. Welcome to my video. In it, I'm going to show why scientists think there was a Big Bang at the beginning of the universe. We're going to look at spectroscopy and the Doppler effect to explain galactic redshift and why that implies that the universe is getting bigger. But let's start with our own little corner of space. Planet Earth is about 7,900 miles wide. The circumference is nearly 25,000 miles. So to drive all the way around the world at a steady 70 miles per hour without even a toilet break would take a little over 2 weeks. Our closest neighbour, the Moon, is a quarter of the size and 240,000 miles away. At 70 miles per hour, the Moon would take more than 4 months to reach. Here comes the Sun. It is so enormous that it is hard to see the curvature. The Sun is, in fact, 864,000 miles across. That's more than 100 times wider than Earth, and the distance between the Earth and the Sun is about 92 million miles. At 70 miles per hour, that would take roughly 150 years. On the scale of your screen, if this yellow dot were the Sun, the Earth would be too small to see in the middle of this circle, which on the same scale is actually as big as the orbit of the Moon. This is another way of looking at it. Here's the Sun again, and comfortably fitting inside is the orbit of the Moon, with the Earth at its centre. The Moon itself is a small grey dot. It is an extraordinary coincidence that the Moon and the Sun appear the same size in the sky. And yet they do, because while the Sun is 400 times bigger than the Moon, it is also 400 times further away. And that means that if the Moon passes directly between you and the Sun is eclipsed. Another amazing fact is the speed of light. Light travels at 186,000 miles per second. That is fast enough to go around the world more than 7 times in 1 second. 7 times around the world is about 3/4 of the way to the Moon. Even at that speed, light from the Sun takes over 8 minutes to reach us. Nah, not going to wait for that. In the course of a year, light travels nearly 5.9 trillion miles, a huge number. So for convenience, that distance is called a light year. Other than the Sun, the closest star is Proxima Centauri. It is 4.25 light years away. The Sun and Proxima Centauri are just 2 among billions of stars in the Milky Way. This is just a bit of it. It's difficult to see the whole thing from the inside, but it is certainly more than 100,000 light years wide. Beyond the Milky Way, the closest large galaxy is Andromeda. It is 2.5 million light years away. It is one of hundreds of billions, perhaps trillions of galaxies in the universe. If you held a sewing needle at arm's length, and if you had telescopes for eyeballs, looking through the eye of the needle, this is what you would see. Each blob of light is a galaxy made of billions of stars, and they are billions of light years away. It's safe to say that the universe is big, but about 100 years ago, using a combination of spectroscopy and the Doppler effect, astronomers were finding evidence that the universe used to be much, much smaller. Spectroscopy is based on the fact that if you shine white light into a prism, what comes out the other side is all the colours of the rainbow, and each colour has a different wavelength. Wavelength is exactly what it sounds like. This red wave is longer than this blue wave. So given 2 steady streams of waves, there are more blue waves than red ones. The blue waves are more frequent, hence the shorter the wavelength, the higher the frequency. Light waves are not really the up and down waves we see on water. They are more like 3-dimensional waves, almost like particles of light. These blobs of light are called photons, but they still behave like waves. The Doppler effect is all about how movement changes the length of photons and other waves. You have probably heard the of something fast and noisy zooming past. That change in pitch from high to low is how the Doppler effect affects sound. Let's look at where the sound comes from. This is inside the engine, the noisy part of a motorbike. The parts involved in making all the racket have been labelled. When the engine starts, the flywheel turns, which pulls the piston down. At the same time, the inlet valve opens and the falling piston draws in a mixture of air and petrol. As the piston continues to fall, the inlet valve closes, so that as the piston rises, the air and petrol mixture is compressed, and just before the piston reaches the top, the spark plug ignites the petrol. The explosion forces the piston back down until it reaches the bottom. This time, when the piston starts to rise, the exhaust valve opens and the explosion races down the exhaust pipe. When the piston reaches the top, we're back to the beginning and the cycle starts again. So the noise of a motorbike is a series of bangs which create sound waves. The number of waves per second, the frequency, determines the pitch. The more frequent the waves, the higher the pitch. The Doppler effect comes into play because the motorbike is moving. That means that as the sound wave of each explosion expands, the next one appears a bit further up the road. So the sound waves are squeezed together ahead of the motorbike and stretched out behind. 70 miles per hour is roughly 10% of the speed of sound. So as the motorbike approaches, the frequency of sound waves increases by 10%. When it has passed, the frequency decreases by 10%, a difference in coming and going of 20%, which is easy to hear. With light, changing the length of photons changes their colour, but whereas 70 miles per hour is about 10% of the speed of sound, it is a tiny fraction of the speed of light. 186,000 miles a second is 670 million miles per hour. 70 miles per hour here or there makes no appreciable difference, but it is there, and with the help of spectroscopy, it can be detected. The colour of light depends on how it is made. This, for example, is the spectrum created by hydrogen. When it burns, the flame you see is made of just these colours. Now, hydrogen makes up about 75% of the sun, so you might expect the sun spectrum to be dominated by the spectrum of hydrogen. But instead of being the brightest bit, the spectrum of hydrogen is missing. That's because the sun isn't burning hydrogen, it is fusing it into helium. Nuclear fusion is for another time. All we need to know for now is that if light passes through hydrogen, exactly the same wavelengths are absorbed as when hydrogen is burned. These gaps are called absorption lines, and every element has a set that is as unique as a fingerprint. In stars like the Sun, the light generated by nuclear fusion in the core has to pass through thousands of miles of hydrogen before it reaches the surface. Galaxies, of course, are made of stars, and when light from other galaxies was analysed, scientists could see the fingerprint of hydrogen, but the light around it was different. In a few local galaxies, the light is shifted to the blue end of the spectrum, but in the vast majority, it is shifted to the red end. As more and more galaxies were looked at, astronomers discovered that the further away a galaxy is, the more its light is redshifted. This implies that the more distant the galaxy, the faster it is moving away from us. Which sounds weird, but that's what happens when things expand. Take this uncooked currant bun, for example. Pop it in the oven. 20 minutes at 200 degrees, et voila! The bun has expanded. Bit of icing, cherry on top. Yum yum. Never mind the bun for the moment. Let's just look at the currants. They don't expand. It's just that they all move away from each other. In an expanding universe, it is galaxies rather than currents which are moving apart. Let's let these letters represent galaxies in a very tidy part of the universe. As the universe expands, the galaxies all move apart. Now we happen to be looking at it from the same point of view as someone, or something, in Galaxy M, which is why Galaxy M doesn't appear to have moved. But to someone in Galaxy A, exactly the same expansion looks like this. Whichever galaxy you're in, it looks like every other galaxy is moving away from you. If we compare the starting points with the finishing points, as seen from Galaxy A, it appears, for example, that C has moved further than B in the same amount of time. So from A's point of view, C has moved faster than B. The galaxy that has moved the most, and the one that from A's point of view has moved fastest, is Y, the galaxy that was furthest from A to begin with. exactly as happens when things expand. Once it was realized that the universe is getting bigger, it didn't take long to work out that it used to be smaller. But how much smaller? Well, as we look back in time, there's no obvious point to stop and say that's how big the universe was to start with. So we carry on until we reach as small can be. Crazy as it sounds, the Big Bang Theory is the idea that the universe is made of some stuff that can grow from practically nothing to billions of light years in diameter. Next time, we'll look at how that Big Bang stuff could become the atoms that galaxies, stars, and even you are made of. If you have enjoyed this video, please give it a like and share it. Thank you for watching.